Hi everyone, we're back to talk about linear differential equations and some examples of models of physical systems that can take this form of a linear differential equation or system thereof. Before we get into the actual kind of models here, let's just build some mathematical machinery with complex numbers that'll make it easier to deal with the solutions later on. So just as a definition, if we have a complex number, we say the real and the imaginary parts, alpha and beta, are notated in this way. And the concept here is that the sum of a number and this overline, which is the complex conjugate, I wrote it here but didn't have it typed, is actually 2 times the real part. So this would be like alpha plus I beta plus alpha minus I beta, so 2 alpha. And then here there's a typo in my notes, but there isn't in your notes. If I do z minus complex conjugate of z, I have alpha plus I beta minus alpha plus I beta, so 2 I beta. And just to recall, Euler's formula says that e to the it is cosine t plus I sine t. So the theorem that we had from the last lecture said that if I have a matrix A, which is diagonalizable, I can find a general solution to y prime as ay as the linear combination of e to the lambda t, where lambda is an eigenvalue, times v, which is the corresponding eigenvector, summed up. And so the idea is that if I had a system where I had eigenvalues that were a complex conjugate pair, and I know my eigenvectors are going to be a complex conjugate pair, I may get some sort of properties that look like this z plus z complex conjugate. So first, we can look at this lemma that says, if I have a complex number here, and I do look at c1 e to the lambda tv plus c2 e to the complex conjugate lambda t times the complex conjugate of v, this should actually be c1 times this vector plus c2 times that vector's full complex conjugate. So let's see why that is. Well, we know e to the lambda t is e to the alpha plus I beta t, which I can split up in this way, and I can pull out this e to the alpha t, and then use Euler's to open up this e to the I beta t as cosine beta t plus I sine beta t. If I have a complex conjugate, I get something similar that I can simplify because cosine is even and sine is odd. So sine of minus beta t is minus sine beta t. And I'll notice if I compare this and the guy above, this is exactly the complex conjugate, right? The minus only appears on the imaginary term. So this is the complex conjugate of e to the lambda t, which means that c1 e to the lambda tv plus c2 e to the complex conjugate lambda tv complex conjugate of v is this complex conjugate, and the product of complex conjugates is the complex conjugate of the product. So we get exactly the result here that we're looking for. So let's use this idea to show that this function, which at first may not appear to be real, is in fact real. And let's make sure we understand what is the form of this function. I have an e to the 2it and e to the minus 2it, so I can think of this as e to the lambda t and e to the complex conjugate of lambda t, right? And then these vectors are also complex conjugates. So it is exactly this form, not only this form that we have here in equation 4, is this form where c1 and c2 are equal. So what we're really getting into is this first kind of concept here, that z plus complex conjugate of z is some real quantity. So let's see why that is. I'm just gonna get off my paper here. Okay, so here we go. So how should we say? We're going to prove it in general. So we can just prove it like with numbers here. So this is cosine 2t plus I sine 2t to I plus cosine 2t, because cosine is even, then minus I sine 2t, 2 and minus I. And the suspicion here, let's write this as two complex vectors. So 2 cos 2t plus 2I sine 2t and minus sine 2t plus I cosine 2t plus 2 cos minus 2I sine. So I have a minus and a minus, so that makes a positive, and then the I squared is a minus 1. So again, minus sine minus I cos. So I have these two complex vectors, and what I want to notice is that this guy is the complex conjugate of this guy. So it's really the scenario that we had on the first page. This looks like a z, this is the complex conjugate of z, right? And in fact, that's true. We should get 2 times the real part, right? Because this cancels with this cancels with this, and I just get 4 cos 2t minus 2 sine 2t, twice the real part of either of these vectors. So if I see a function that has, some certain forms, like this guy here, maybe I will simplify it and say that looks complex, but it is actually real. We have models where we'll be looking for real solutions. So showing that could be a helpful thing. So let's see, we kind of go through this on page 3 of the notes in a more general form, writing out exactly just kind of what we did, but this is for a C1 and C2 that don't have to be equal, and we end up with C1 plus C2, the real part, and then C1 minus C2 times the imaginary part, which we can redefine as some new constants, D1 and D2. Great. So let's transition to solving some initial value problems, some differential equation here, and see how that relates to this. So here's the problem that I want to solve. And if you remember, well, if you don't remember anything, then what you should think of is I need to find the eigenvalues of this matrix, right? That is like the default of what we do. But if you do remember, we'll say, okay, I have y prime is equal to AY, so I need to find the eigenvalues and the eigenvectors, and the solution looks like a linear combination of e to the lambda t v for the 2 different lambdas and v's. And then I can find the constant C1 and C2 of that linear combination using the initial condition. So that's the plan. So 1, find eigenvalues. So I have lambda minus 2, 5 minus 1, lambda plus 2. I need the determinant of that matrix. So I have lambda squared, plus and minus 2 is 0, so then minus 4, and then minus minus is going to be plus 5. So I have lambda squared plus 1 is 0, otherwise known as lambda is plus and minus I. All right, complex conjugate pair. So let's find the eigenvectors. In fact, we only have to find one eigenvector because the other one should be its complex conjugate. So if I have that lambda is equal to I, this equation up here starts to look like minus 2 plus I, 5 minus 1, 2 plus I. So that times x1 and x2 should be 0. And so what should that eigenvector be? What is the trick here? What's the multiple? So the equations to solve are minus 2 plus I, x1 plus 5x2 is equal to 0, and minus x1 plus 2 plus I, x2 is equal to 0. It's not immediately evident to me what we're looking for. So let's just say this equation is x1 is equal to 2 plus I x2, and plug it into the first equation, which means minus 2 plus I times 2 plus I x2 plus 5 x2 is equal to 0. Let's multiply that out. So that's minus 4 minus 2I plus 2I. So minus 4 and then minus 1 x2 plus 5x2 is equal to 0. So this equation just gives us 0 is equal to 0. That's not so helpful, right? I guess that makes sense because these should be the same thing, I guess. You know, these two rows should give us maybe an equivalent condition. So what's the condition? So if x1 is equal to 1, and x2 is equal to 2 plus I, does that work? Oh, sorry, flipped. Whoops. That's why that didn't make sense. If x2 is equal to, I'm taking this this property right here. If x2 is equal to 1, so let's look at this equation. That would certainly work. And then the top one, 2 minus I times, or minus 2 plus I, this is going to give us minus 5 and then plus. Okay, I think that's fine. So this is my eigenvector. Okay, so what does that mean the solution looks like? General solution. So y is going to be c1 e to the it times this eigenvector plus c2 e to the minus it times its complex conjugate. Here we go. Looks great. And the last thing is to solve the initial value problem. So if I plug in y of 0, well, maybe before that, I can say this is z and z complex conjugate. So this is really 2 times the real part of any of these. So what's the real part of this? So it's really, with another constant. Okay, so maybe that's not as helpful. But I still know one thing. I know that this is going to be real, right? I have some other constants like d1 and d2 in the concept above in equation 9. Maybe I'll just solve it this way. So when I plug in 0, I get c1, and that's e to the 0, 2 plus I plus c2, 2 minus I, and that has to equal 5, 2. So, I think a nicer way to deal with this is to make this into a matrix form. Equivalent, right? So this is this inverse. So 1 over the determinant, 2 plus I minus 2 plus I. So 1 over 2I is the determinant. Is that right? I think so. This guy. C5 minus 4 plus 2I minus 5 plus 4 plus 2I, 1 over 2I outside. And so I get 1 plus 2I minus 1 plus 2I. That doesn't look real. Hold on just a sec. Hi, we're back. I got myself a little bit confused because I was thinking these should turn out to be real. Of course, the coefficients don't have to be real, right? Just the solution. So we're all fine. So if we finally finish this calculation for C1 and C2, this looks like 1 over 2I plus 1 and minus 1 over 2I plus 1. Remember, 1 over I is negative I. So I can finally write this as 1 minus a half I and 1 plus 1/2 I. Now that I is no longer in the denominator. Great. So how is this helpful with what we learned above? Because now I have some complex looking function in the box here and complex looking coefficients. Certainly doesn't look real, but by equation 9, way upstairs here, I know that I can write this as C1 plus C2 times the real part plus I times C1 minus C2 times the imaginary part. And that should be my solution here. So C1, oh, maybe over here we'll say, what's the real and the imaginary parts, right? So make a little box. The real part of e to the it, 2 plus I1. What is that? So that is, we have the real part of cosine t plus I sine t times this vector here. So the real part should be 2 cosine, right? And then minus sine, because I times I sine. I don't care about the imaginary parts, and just cosine t for the second element, right? And the imaginary part of e to the it, 2 plus I over 1. If I look at this, the imaginary part is going to be 2 sine t plus cosine t, and then sine t downstairs here. Okay, so the final solution here should be C1 plus C2. Remember what C1 and C2 are over here, C1 and C2. If I sum them up, it's 2. So 2 times the real part, 2 cosine t minus sine t, and cosine t as the second element, plus d2 is going to be the difference of these guys. So C1 minus C2. So I have minus 1/2 I minus 1/2 I. So just minus I. And then that's going to be times I. So minus I times I just gives me 1, right? So that's my d2 times the imaginary part. So that plus 2 sine t plus cosine t and sine t by equation 9. So this gets me to a real form in a pretty succinct way. And it is worth noting that the solution really looked imaginary, right? before. It was not really evident that this was real. So that can be some helpful trick and manipulation. So let's get to how these differential equations can be used to build mathematical models. The first one we're going to look at is going to be a harmonic oscillator, damped and undamped. And the second one we're going to look at is going to be a two-tank problem. You might remember from differential equations class. Okay, so now we're on page 4 of the notes. So the first example is that we want to talk about Hooke's law. So Hooke's law is used to model, it's used to model a spring. Hooke's law says that the force generated by a spring is proportional to the displacement. So whether the spring is extended or contracted. So let's suppose we have, this is how we draw it in engineering, some fixed surface. We have a spring, this is the spring, and it's hanging. At the bottom is a mass. So we call this a mass spring system. And the mass has some displacement, call it x. This is displacement, where the arrow points in the positive direction, and so that's downward. The spring has a length of L, and it doesn't have a negligible weight. Great. So if the spring is stretched or compressed, I guess this L comes before I even put the mass onto it. If the spring is stretched or compressed, then we get this restoring force that is proportional to the amount of stretching or compression. So that's this restoring force here, where delta x is the displacement, and k is some constant, the proportionality constant, and it's minus because this constant is always positive. So that means that when delta x is positive, so the spring is stretched downward, the restoring force happens in the negative or upward direction. So it's in the opposite direction. And then when the spring is compressed, so delta x is negative and the mass is pushed up, the restoring force is positive. And so it pushes the mass back down. So restoring is always in the opposite direction here of the displacement. So the spring constant has units. It's dimensions of force per unit length, so like newtons per meter. And it measures the stiffness. So the larger the K, the stiffer the spring. You can imagine what that means. If K is bigger, it means for a smaller displacement, you get a larger force. It's like a really hard to move spring. The opposite is what we call a soft spring. That's where you can move it a lot, stretch it a lot, or compress it a lot, and it doesn't give a lot of restoring force. That's like a slinky. Slinky. Slinkies don't have, they're not very stiff springs, right? They kind of flop all over the place versus like a really stiff spring like you would have in your clicky pen, right? It's pretty stiff. You press it even a little bit, you get quite a bit of force. Okay, so now we're going to add the mass. Let's go back to our picture. Now we have the mass hanging on the end of the spring. And so this is L without mass. Now, when we put the mass on, the spring gets stretched and starts to hang down. So how far does it hang? Well, that's going to depend on the weight G, or the weight M, sorry, of the mass, and gravity G. So the mass has a certain weight, and we know that when we put the mass on and the spring is still in equilibrium, we're going to get some balance between the weight of the mass and the restoring force provided by the spring. So this is in equilibrium. I put on the mass, the spring becomes still, and this must be, this must describe the position of the spring. So mass is fixed, gravity is fixed, K is fixed. But this allows us to understand this, what we call equilibrium position X, this displacement X, which is kind of the new stretch position of the spring when the mass is on there. So that's what we have in equilibrium. But then, if the spring starts to move, if the mass is displaced, so you have this mass, you pull it down, and you let it go, we get dynamics. The dynamics are governed by Newton's second law, right? F equals ma. The force is proportional to the acceleration, where mass is the proportionality constant, right? So we have something that looks like second derivative of x times the mass, and then we sum up all the forces on the right-hand side. So what's the position? The position is going to be x, the equilibrium position, times this new coordinate little x, or sorry, plus this new coordinate little x, second derivative of this times m, and then is equal to the two forces. What are the forces? We have the weight of the mass and the restoring force of the spring. Here's the weight of the mass. The restoring force of the spring is proportional to the displacement, which is now big X plus little x. So big X is a constant. I'll write that here, constant. Great. So that means the second derivative is 0. So I just have mx, a second derivative of x. I would prefer this actually when we make these dots in your notes, because that's usually how we put time derivative. So I'll change that for the ones that you print out. So mx double dot is equal to mg minus k big X minus k little x. But we know this is equal from the equilibrium, right? That equals 0. So really, the equation I get is mx double dot is equal to minus kx, or this much more notorious form, mx double dot plus kx is equal to 0. This is a really famous equation. This is called the equation of motion for a simple harmonic oscillator. So this is something that moves only in response to a restoring force. So it doesn't have what we would call damping, anything that would stop any oscillation. So this could describe like a pendulum without friction, or a mass and a spring without friction, these kind of idealized things. And these are things that when you pull the mass down, let it go, and then it will oscillate forever. This very ideal physical system. Okay, so that's the mass spring system. Now let's suppose that we provide something that will give a damping in the system. So damping is something that dampens oscillations. So sometimes we call it a dash pot or a damper. Could be, like some sort of prismatic joint that has an oil in it, that the viscosity of the oil absorbs some of the energy in the system, and so it will dampen the oscillations, this kind of thing. And the way that I put that in the drawing, if I go back to page 4 of the notes, it has this kind of funny look here, like a straight line, and then this kind of box around it. A lot of times you draw a K next to the spring for the constant there, and then depending on what the damping constant is, what do we use? Gamma. Put a little gamma next to the damper. So the spring is the squiggly guy, and this guy is the damper. The other word for it sometimes is the dash pot. Okay, so there's a lot of different ways to model damping, but a very common way is what we call viscous damping, wherein the damping force is proportional not to the displacement, but to the rate of change of the displacement, or the velocity. So this is called viscous damping. There's other models of damping, just so you know. This is a really common one. Okay, so this again works in the opposite direction of something, but it's not in the opposite direction of the displacement. It's in the opposite direction of the velocity of the mass. So if I add this into our Newton's second law equation, now we have equation 17. I have m times the second derivative of the displacement. It's going to be equal to the sum of the forces. The forces are now weight plus the restoring force provided by the spring, plus the damping force provided by the damper. So the weight is mg, minus kx plus x is the restoring force, and minus gamma ddt of x plus x is the damping force. So we know these terms here are going to cancel, and we know that the derivative of d capital X is equal to 0. So we get this other kind of famous equation for not a simple harmonic oscillator, but what we call a damped oscillator. Great. Awesome. So if you ever do like a physics or dynamics class, you're going to see an equation that looks like this. We're not going to talk about it too much in general, because that's kind of outside the scope of the class. I just want to let you know that like these equations exist, they're really famous and people have studied them. So depending on the m and the gamma and the k, you can make this look like a lot of things. The m usually is kind of fixed, provided by the system, but the things you may tune with a given m would be your gamma and your k. How stiff is your spring, and how strong is your damping force? Because you can have things like a very strong damping force, so that when you displace the mass, you pull it and let it go, there's no oscillation. It just zooms back to the equilibrium position and stays there. Or you could have a really weak damping, and so you get very long sustained oscillations. It takes a really long time to die out. So you can have different kind of trajectories for the system just by changing these gammas and k's. Let's consider one system with certain gammas and k's. We're on page 6 now. So we have mx double dot. Get rid of those apostrophes. I don't like them as much. Usually we use dots for time derivatives. That's what it'll be. And I am going to look at mass spring damper, x double dot plus 2x dot plus 5x is equal to 0. Let's understand what solutions of this look like. Let's solve it, but then also talk about the physics, because of course this is a mathematical model. So first we have to convert the second order system into, the second order equation into a first order system, a system of two first order equations. So I'm going to say x1 is equal to x, x2 is equal to x dot. So just by this relationship I've defined, x1 dot is equal to x2, right? So x dot is equal to x2, and x2 dot, well, from the equation above, it's going to be move all these guys over to the right-hand side. So minus 5x1 minus 2x2, and I'm going to want it as a matrix equation. This is x1 dot x2 dot is equal to 0, 1, minus 5 minus 2, x1, x2. This should be really familiar from your differential equations class. Okay, part 2 says apply stability analysis to the first order system and say what does this tell us about the limit as t goes to infinity of any solution x of t, right? Well, I guess, no, just x, not the vector, just x. Okay, so what we saw last time was that whether or not solutions were stable only depended on the sign of the real part of the eigenvalues of this matrix. Call it A. So as with everything in this class, let's find the eigenvalues of A. So lambda minus 0, minus 1, minus 5, lambda plus 2. So I have lambda squared plus 2 lambda plus 5 is equal to 0. And so I don't know what the factoring is, so we have negative b plus or minus squared, b squared minus 4 times a times c all over 2a, so minus 1 plus or minus, let's see, what's this? This is minus 16, so 4i, so divide that by 2 is 2i, right? So the eigenvalues are, lambda is -1 plus or minus 2i. So from, oops, I'll move it up a little, the last lecture, we know the real part of lambda, now it's less than 0, implies that all solutions go to an equilibrium, global asymptotic stability. Global asymptotic stability, stability of an equilibrium. So that implies that x of t goes to x star, some x star, as t goes to infinity. So I'm going to have some solution that all of the equations, all of the solutions decay to. And given the form of this guy up here and the fact that A is full rank, the solution should be the origin, right? So since the determinant of A is non-zero, x star should be 0. Okay. So part 3 says, let's go ahead and solve the initial value problem that governs the equation of motion of this block. So this is what we looked at before, but now I just have initial conditions for both the position and the velocity. Okay, so let's get to this. So I already found the eigenvalues. So let's find the eigenvectors. We know a solution should look like a linear combination. So if I had that lambda is equal to -1 plus 2i, the matrix equation to solve is -1 plus 2i minus 1, 5, and I have now 1 plus 2i, x1 plus x2, 0, 0. So if I just do v is 1 and then -1 plus 2i, just looking at the first row, let's see if that works. Right, because in the first row, if I do this times 1, this is the negative of this, and then -1 times whatever this junk is, and I sum it up, I should get 0. Let's see if that's the case for the second row. All right, check. So I need to check that 5 times 1 plus 1 plus 2i, and now -1 plus 2i, multiply those. Is that 0? So it's 5 plus -1 minus 4 and one. Oh, right, and then I have plus 2i and minus 2i. This one times this one. Great. So that equals 0. Check. So that's going to be my eigenvector. So my solution here, x1, x2, should look like c1 e to the -1 plus 2i times t, oops, I drew that a little too high, times 1 minus 1 plus 2i plus c2 e to the -1 minus 2i t, 1 minus 1 minus 2i, the complex conjugate. This is my solution here, my general solution. When I plug in the initial condition, what should I get? So that I see 2 for the position and 2 for the velocity, so that's easy. Is going to be C1 times this guy plus C2 times this guy. So 1, I'll do it again like a matrix form, find that easier. Minus 1 minus 2i, C1, C2. So C1, C2 is going to be, what's the determinant? Minus 1 minus 2i minus a minus 1, and then so 1 over minus 4i, right? Is that right? Yeah. Minus 1 minus 2i, 1 minus 1 minus 1 plus 2i times 2. I'll write this as, so there's a minus and a 1 over I, so that just becomes an I. So this is 1/4 times I. And then I have minus 2 minus 4i minus 2, and minus 2 plus 4i plus 2. So the first element is minus 4 minus 4i, but I have it divided by 4, so minus 1 minus I minus 1 minus I, and then I just have 4i, so divided by 4, just an I. So what am I finally left with? I times minus I is 1 minus I, and then 1. Ooh. All right. Still doesn't necessarily look real, but x1 and x2, I can do the same trick that I did before. This is going to be by equation 4 here. It's going to be C1 plus C2 times the real part of whatever this junk is, plus I times C1 minus C2 times the imaginary part of whatever this junk is. Okay, so C1 plus C2 is going to be 2 minus I, 2, oops, sorry, I times I should be a minus 1. C1 plus C2, so let's first see, just 1 second. Okay, so we're looking at this C1 and C2, and we have a little mistake here that you may have caught. So I was solving this equation here. Did 1 over the determinant to get the inverse. I switched these 2 entries here, but I should have made the 2 off diagonals negative. This one didn't become negative, so this should be a plus and a minus. Great. The first row up here is right. The second row should be 2, positive 2 minus 4i plus 2. And now this is good. Now we have 4 minus 4i. So when we divide by 4, I have 1 minus I. Great. And now when I multiply by I have 1 plus I. 1 plus I. Great. Why do I care about that? It's because these had better be complex conjugates if I want C1 plus C2 to be real. Okay, so now we're back to using equation 4 down here. C1 plus C2 is just 1. Okay, what's the real part? We do some work right down here on the side of this plot, which we'll talk about in a second. What's the real part of e to the lambda t v? So e to the lambda t is e to the minus 1 plus 2i v. 1 minus 1 plus 2i. So oops, I forgot the little t there, t. This is e to the minus t, and then cosine 2t plus I sine 2t times this vector. Okay. So there's always an e to the minus t. And I have cosine 2t plus I sine 2t as the first element. The second element is going to be minus cos 2t minus 2i sine 2t, right? Oh wait, sorry, no I. I did the 2i times I sine, so no I. And then plus I times minus sine 2t plus 2 cos 2t. Great. So the solution here, well, I guess this isn't the real part necessarily, this is the whole thing. I can see what the real parts are, this and these, and the imaginary parts here. So from equation 4, c1 plus c2 times the real part is 1 e to the minus t times cos 2t minus cos 2t minus 2 sine 2t plus c1 minus c2. So this guy minus this guy is going to give me minus 2i, right? Then times another minus I, minus 2i, or sorry, times another I. So a minus 2 I squared, which should just give me 2. 2 e to the minus t times the imaginary part of this equation down here. So sine 2t minus sine 2, minus 2 sine 2t, no, just minus sine 2t plus 2 cos 2t. This equation is for the position. This equation is for the velocity. Now I know the full story. This is a little hard to see. This is just a, scratch that all out, just a minus sine 2t. So hopefully that is clear. And it all looks okay, except did I do C1 plus C2 right? I don't think so. C1 plus C2 is going to be 1 minus I plus 1, so it should be a 2 actually here. Okay, now we're in business. Now we have an equation. And in fact, we can see here in the plot below what this plot should look like. So this top equation is 2 e to the minus t cosine plus 2 e to the minus t sine. So like this. I start at 2 with a slope of 2. What happens to the system? I get some oscillation, and it slowly, maybe not so slowly, peters out to nothing. Right, it's got a big up, a little down, a little up, and then looks like it's pretty flat. So this looks like the motion of a damped oscillator. Okay, great. I'm going to stop the video here and then we'll do one more example in the second video.